Hi, my name is Andrew McLaren, and I'm going to help you with Hess's law, which has to do with when you have these different changes of H, or that enthalpy of these different reactions here, and that you're trying to then determine a new reaction's change in enthalpy. So this is a very common question type that you see in like AP Chem and College Chem. So I want to spend some time going over like the big picture on this, as well as like easy, medium, and a hard example. So we'll just kind of talk about these things in terms of just general concepts of reactants and products. And then we'll actually look at a couple different example problems, some that are a little bit easier and some that are a little bit harder to do. So to get started with Hess's law, we need to do a little bit of review of enthalpy. So if we have a reaction and you have some reactants that have some sort of level of energy, then you have some products that have a different level of energy. There's a difference between them, and this is often called change in H. And it's really important to understand what these change in H values really mean in terms of energy flowing in or out of the system. So when you have something that looks like this, and you've got a change in H that goes up, this is a positive value. So we're saying that there is energy kind of coming into the system because you're going from these reactants to these products. And so this is a gain of energy when we have a positive change in H. And then when we have something that is the opposite, we could think of this as now when you have some reactants going to some products down here, there's going to be a change in H value there that is negative. So that is going to lose energy. And one of these is going to be spontaneous and one is not going to be spontaneous. So you can think of a ball rolling down a hill as being spontaneous. So when a ball rolls down a hill, that's going to be spontaneous. When it has to get pushed up a hill, that's not spontaneous. That takes some energy to do that. It's not going to happen on its own. So we would say that this is not spontaneous, but we would say that this is spontaneous, aka this happens on its own. And so what we can then talk about is the broad idea of these things being different heights. And so you can think of when you are at some reactant and it goes up to some sort of higher energy product, that is going to be a change in H that's positive. And then when you have some reactant that's a higher energy than some product, yeah, the reactant that's higher energy than the product, then the change in H there is negative. Now these values should be negative numbers for both cases. Like this should be a negative number, and the same for the amount of product. That should also be a negative number for almost all chemicals. When they are formed, that has to release some energy. So these are negative values that you're going between from going from reactant to product. But the change in H might be positive, negative. It might be like, let's say that this is, I don't know, like -10, and that this is -20. So if you go from -20 up to -10, then that change in H would be a +10. So that's the big picture on these problems in terms of enthalpy. And then what we're going to then do is consider if you've got these different reactions and how their changes in H react of these different reactions relate to a new third reaction. So if I have like A um, going and forming some product B, this is like the first reaction, we could have a change in H value there. Maybe this is going to be like a +10 change in H. And then we've also got another reaction that say that this is kind of like C going to form B. Then this is going to have a change in H value of, let's say, also a positive. Let's do like 15 now. So we've got a +10, a +15, when these two reactions are just looking at as is. So we could think of this as like A kind of getting up a hill, right? So that you could think of like A is down here and B is up there. So that change in H value is a +10 going between here to there. Then you can think of this as like C now going up to B, and this is a positive 15 change. And you can see that like, okay, well now if I want to go from A to C, we should be able to think about that relationship here where it's like, oh, C had to go further up to get to B. So if we wanted to then kind of combine these, you could see that like B going down to C, that would be like a negative 15. So C is kind of down here. So what we do mathematically speaking is I would say like, okay, I've got like line 1 and line 2, and I'm going to want to flip line 2. So line 3 right here is actually going to be a negative of line 2. And when we do that, we end up getting something that looks more like B forming C and a change in H value that's now a negative 15. Because if it was positive 15 to go up to B from C, going from B down to C should be a negative 15 in terms of that energy release. So you could say that this is a negative of that number, and I didn't have to change any of the moles because these are going to be in kilojoules per mole. So I'm saying like 1 mole of A will react to form 1 mole of B, and that will release 10 kilojoules, or 1 mole of this reaction basically happening. So if I want to then, if I were to multiply some of these, we'll do that more in the second part, then you might have to multiply the change in H. But in this case, we're just changing the change in H's sign because it's just a flip of those two. So then if we take our line 1 here, that works out nicely being combined with what we have as line 3. And you can end up getting a new final reaction. I'm going to call that line 4. Line 4 is going to be 3 plus 1, like line 3 plus line 1. And when we do that, then we end up getting something that's going to be more appropriate to combine. So if we have A now being combined with B, that's these two right here. Those are our two reactants. And now we've got our two products here. So that's forming a B and a C. And as you can see, these B's, if you've got something that's present as both a reactant and a product, they get canceled out. And you're left with this new reaction of A going to form C. And now this change in H is just going to be a matter of combining the negative 15 kilojoules per mole with the positive 10 kilojoules per mole. And we should get a negative 5 kilojoules per mole in the big picture here. And you can kind of see that. I'm going to just change this all so this is purple. But you can see that change in H here. This new reaction of going from A to C. So that's the big picture, is that you can kind of switch the change in H because now we're having the inverse reaction. So instead of going up a hill, it's coming down a hill that certain amount. And that's pretty nice and easy when you're just flipping the sign of one of them. Typically, that's not going to be the case for most of these problems. They're going to make you work with multiples or something like that. So if we were doing this, maybe we've got X going to form Y, and that's going to have a change in H value. Let's say that that is now negative 20. And then let's say that you've got 2Y, and that's going to form 2Z. And I want to know what the change in enthalpy would be going from X to just 1Z. And let's say that this change in enthalpy is now plus 10 kilojoules per mole. But this is kilojoules per mole of the reaction. And this is also kilojoules per mole, but of its reaction. So you can see that this value is for 2 moles of Y to form 2 moles of Z. So this is kilojoules per, actually 2 moles of Y and 2 moles of Z, because that's like the kilojoules for that reaction. So if we're trying to get to here, I'm going to, in a similar way, I'm going to call this line 1, I'm going to call this line 2, and I'm thinking that instead of working with line 2, I'm going to want to get half that value. So line 3 here is now going to be line 2 divided by 2. And so if we look at that, then we can rewrite line 2. That's going to be now y going to form z, and its change in h value now is going to be half of what it was. So instead of positive 10, this is positive 5 kilojoules per mole of that reaction. And you can see that line 3 and line 1 now kind of cancel out. If you take for line 4, you can say I've got line 3, and I'm going to add that to line 1. And when I do that, things cancel out kind of nicely. So I'm seeing that we've got, if I rewrite line 1, I can just, because we're using the interactive whiteboard, do a little trick there. It makes this just a little bit easier for us to focus in on these lines. And so you can see that the y's are end up canceling out. But we've got this y and this z as reactants. We've got x plus y right there. And then they're going and forming some y plus z if we end up just adding those two as is. But as you can see, the y's cancel out like what we saw above. And we get this x to z. And it looks like it was just combining what we had as line 3 and line 1. So you can end up getting that change in h value by looking at the negative 20 plus the 5 kilojoules per mole, and we get a negative 15 kilojoules per mole of this reaction, number 4. So that's the main idea, is that you're trying to cancel things out, and you're going to probably have to cancel things out by either flipping the signs, which correspond to these things now being the opposite reaction, so they're kind of going up the hill or down the hill a certain amount, or you can think of them as maybe having to multiply or divide by a certain number of energy, because if you've got more reactant, it should be releasing more energy if it's forming some product in an exothermic reaction, or vice versa if it's endothermic. So just to kind of solidify this, you can kind of see reaction 1. If we were trying to draw out reaction 1, that was where we had this reactant, which was X here, and then you had some product, which was Y there, and it was going down 20. So I'm just going to make this a simple hill, so that's like negative 20. And then if we were looking at reaction 2, you can think of that as something where you had like 2 Y's as your reactant, and then that was going up, it looks like, to a positive 10 joules. Yeah, so and then that was to 2 Z's, which were your product, and to do that, that was a positive 10. But if we really want to have this thing cancel out 1 mole of Y with 1 mole of Y, then this was not appropriate, because we had 2 Y's and 1 Y. And so you want to be careful. Instead of line 2, I would want to imagine what we've got as line 3 here being the same sort of idea, but now you've got just 1 Y going up to 1 Z, and that energy change is plus 5. So this is more appropriate to then kind of think about how this is kind of going up now, plus 5. And that is kind of what we did with combining steps 3 and 1. Right, this is kind of getting that change in H value that we're seeing that makes more sense, where it's like, oh, this went up 5, but it was going down 20. So that's quite a bit more down than up. So the big picture for this change in H here is going to be down 15 kilojoules per mole. So that's how these things generally work. And typically you're going to have to do both these steps in a problem where you're flipping something and then multiplying or dividing by something in the big picture to cancel things out to form this new reaction. All right, so this is like the easy example, but even still, it kind of looks complicated. Most of these problems aren't going to just give you something easy where you're just flipping one thing or multiplying one thing by a half. There's probably a couple different steps. But what I would highly recommend that you do here is kind of look at what's in these things and are they on like the correct side. So do we have them as reactants or do we need to make something be a product that is a reactant? One thing that I would also encourage you to do is to kind of mark this up. So I can see like that is like that's correct in terms of the right size and the right number of moles there for that SO3. I'm pretty happy with that. I don't see SO3 in any of the other reactions. Like these other two are just, they don't have SO3. So that looks like what I'm going to call line 2 is good as is. So then I'm also looking at like there's one water molecule here, but there's water being used in multiple steps here, so it's a little bit messy. Luckily though, this is water as a gas. So water as a gas, that looks like that's in the correct side. So line 3 looks like that's pretty good. And I'm seeing that these waters should cancel out as well, the water liquids, as is with how we've currently written them. Then if we have this H2SO4, I am going to realize that that is actually on the wrong side. So we're going to have to flip this. Just looking at that visually, I can see that that one is probably going to need to be flipped. So line 1, I'm going to actually rewrite that one. And I'm going to call this line 4. And so I'm going to end up just flipping everything basically. So now we've got H2SO4. And I'm going to just drop the states of matter for these things just to save a little bit of time. But you could imagine that we could add those in as well. So line 4, this works out really nicely, and it looks like it's going to cancel out with some stuff from line 2 as well. But line 4, it's changing H now. We need to flip that sign. So that's going to be a positive 235.5 kilojoules. And this is really kilojoules per mole or for the reaction there. And it looks like line 4 and line 2, if we want to combine those, that should cancel out pretty nicely. So I'm going to call this, we could do this in multiple steps, but I'm going to call this line 5. And line 5, to me, it looks like it's going to work out nicely if we just combine like what we've got as line 4 and line 2 and line 3. Line 5, I'm just going to do is one step. I'm going to combine line 4 and line 2. And so if we do that, then we've got the H2SO4. That's one of our reactants. And then we're combining that with line 2. Looks like we're having the H2S plus 2O2. And then that's all of our reactants. Yeah, we've got that, that, and that all taken care of. And that's our reactants. So now we've got to get our products. And we can see that we've got this H2S right there, plus the 2O2 right there. And then we also have our SO3, which I'm seeing in, what is that, line 2 right here. And our water, I am going to write that as a liquid because its state of matter is important in canceling things out a little bit here. So line 5 worked out pretty good, but now I'm seeing that there's a couple things present with the same number of moles on both sides. So you could think about this as subtracting 2 amounts of water from both sides, or excuse me, 2 moles of oxygen there, and they cancel out nicely, leaving us with just our H2SO4 and its SO3 plus this H2O as a liquid. So those work out almost to the point where we have what we're looking for. Not quite, but we could then look at its change in H value. So line 5, it was combined by looking at line 4, which was a positive 235.5 kilojoules. So that was the line 4. And then we added to that line 2, which is a negative 207. So if we then combine those two numbers, then we can just do that with a little calculator work. 235.5 minus 207. That looks like that's going to be 28.5 kilojoules. So it's a positive 28.5. That seems pretty appropriate given those two numbers that we combined and that we had to flip the first one in line 1 to get as line 4 to make that be positive. So then I'm thinking like, okay, well, I've got my line 5. That's looking pretty good. But I'm going to need to combine that with line 3. And I'm pretty sure they just cancel out as is. So I'm going to call this line 6. Line 6 is just adding these two together. So we've got line 5, which is the H2SO4, going and forming SO3 and water as a liquid. And that's going to be like what we have for the 5th line here. But we're going to need to combine that with line 3. So I'm seeing with line 3 that there's some water as a liquid right here, being combined with this H2SO4. That's a liquid there. And then I'm seeing also this water now as a gas. And it looks to me like that works out pretty nicely with the canceling. So we can see that the water that's a liquid gets canceled out on both sides. And this leaves us with our final reaction that we're trying to make. The H2SO4 going and forming the SO3 and some water that is a gas. So that does work out nicely, but then we need to take note of our change in H for line 6. That was just a combination of line 5 and line 3. So we have the positive 28.5 kilojoules from line 5, and we had line 3, which was a positive, looks like 44 kilojoules. And so these work together. It's kind of like going up a hill and then another hill in terms of that energy. And so this is a very positive number compared to those previous two. So instead of 28.5, now it's that plus 44. So we're left with 72.5 kilojoules as a positive number. And that's the main idea on these problems. Now, I would encourage you to rewrite the lines out and use color coding on this. It just makes it so much easier to keep track of what's where. And we could have done like, okay, flip the sign on this number, then add it to that number, and then add it to this number. But most people, it's juggling too much mentally. So it's easier to kind of write out the different steps. You could have done like line 6 was like an alternative way of doing this problem would have been kind of skipping what we did for line 5 there and doing a different line 5 where that was line 4 plus line 2 plus line 3. And that would have been totally valid because that's what we kind of did in 2 steps, but you could combine all of those in one if you're seeing things cancel out. It's just a lot to do all at once. So I would encourage you to break it down into steps that you can follow a little bit easier. So this question is a bit harder because things don't cancel out quite as nicely as on the previous problem. And I'm going to write out all these different lines. So what I'm going to say is that I have line 1 here, line 2 here, and I'm ultimately trying to make this reaction. And like I saw on the previous problem, some of these things are kind of in the right spots. Like if I'm looking for CO2, CO2 is right there. And so that one is looking like that probably doesn't need to be flipped or multiplied. So I'm liking the look of 1. But when I look at line 2 there, I'm like, that doesn't seem to work out as nicely because I'm seeing that there's 2 CO2s here and they're on the wrong side. And they also are going to need to be multiplied. So we're going to have to flip line 2 and also divide it by 2. So I'm going to do that as 2 different steps, although you could do that as 1 step. It's just a little bit easier for my brain to do that way. So if I've got line 2 and I want to do like a negative of that, I'm going to call that line 3. So line 3 is just going to be like the reverse of line 2. So in that case, then I'm going to take 2 COs and I'm just going to drop the states of matter because it's not as critical in this problem as what we saw in the last problem. I'm seeing 2 carbons and this oxygen written as just 1 mole And so if I'm flipping that, now its new change in H is going to be flipped as well. So we've got a positive 221 kilojoules per mole. And see, they're even doing kilojoules per mole in this problem, which is more appropriate because this is the amount of energy per amount of matter, and that can help you with understanding how this needs to be multiplied or divided. So I can see that I probably want to cut these numbers in half. So I'm going to call this now line 4, and it's going to be kind of like line 3, but now divided by 2. So when we do that, now we've got CO going and forming carbon and a half of a mole of oxygen. And that change in H then is going to be that 221 divided by 2. And we can then get that number pretty easily. So that's going to be a positive 110.5 kilojoules per mole for that line 4. So line 4 is looking pretty good. It's got I've got that CO on the correct side there and the correct number as well. And we've got the CO2 on the correct side with line 1. So I've got a feeling that if we take line 4 and we add that to line 1, then that would work out nicely and give us what I'm going to call line 5 here, which is, I believe, the final reaction. So if we look at that, we can see we've got the carbon monoxide, and then we've also got this carbon, the 1/2 oxygen, and then we also have this reaction from line 1. So if we add those reactants, just going to give us a little bit of space to get the reactants. So we've got the reactants from line 1, which is that carbon, and the old O2. It looks like there's 1 mole of that O2 there. And that will then form, 1 carbon dioxide. And that looks good. Like we've taken line 4 as is, and we've taken line 1 as is, and everything's on the correct side. This is why I like to rewrite this stuff out a little bit. So that is our line 5. Just gonna change that to gray just to help my brain a little bit. And I can see that the carbons cancel out, but then you're going to subtract 1/2 O from both sides, or 1/2 O2, and so that gets rid of the O2 on one side, but then that leaves you with a 1/2 oxygen on our reactant side, 1/2 oxygen gas, that diatomic gas. And I believe that that is our reaction that we're looking for. I'm just going to double check that. Yeah, I've got carbon monoxide, 1 mole of that, 1/2 mole of oxygen gas, and 1 mole of carbon dioxide. So that looks good. And now I can think about, well, my change in H came from line 4 just being added to line 1. So I have those numbers with the correct signs there. So that's a positive 110.5 kilojoules for line 4. And that was being added to a negative 394 kilojoules for line 1. When we add those two numbers together, we've got that as a positive number, so let's just subtract 394 from that. We get 283.5 is a negative number, kilojoules. And so this is looking like that's our option B there. So we're able to get to our final answer there. Now, I got this from a student that I was tutoring, and you can see that they're trying to do like too much mentally without writing it out. And so they made some silly mistakes with the numbers. If you rewrite the lines out and kind of keep track of it, it may take a little bit longer, but it is so much easier to check and kind of understand what went wrong if something did go wrong. All right, now we're gonna be doing one that's a little bit harder. It's very similar to the medium example where you gotta just kind of keep track of your work. And if you write out the lines, this is gonna be very, very useful. So like we talked about on those previous problems, we're gonna look for things that are kind of like on the correct side, maybe with the correct number of moles. Unfortunately, I'm seeing HCl in multiple places there, so I'm not gonna start with that. So that's just like not a good option trying to balance that out because it'll get affected by one reaction being balanced out will affect the other reaction, how many you need to cancel out with. So instead of doing that, I'm going to look for maybe the the B28H6. And it looks like that's only present in one reaction and it's 1 mole. So that looks pretty good as is. So line 2, I'm like, yay, I like line 2. Then I'm looking for like Cl2. I believe that's only present there. Oh, it's only 1 mole of that. Yay. Line 3 looks pretty good as is. And then I'm looking at this line 1. Line 1 has some issues. So I'm seeing that there's BCl here. We're wanting there to be 2 times that. So line 1 kind of gonna have some problems there. So we're going to need to flip that. And we're going to need to divide it by 2 to get this final reaction. Now the HCl's, I know they're going to end up canceling out. We'll have to prove that as we do the problem, but I'm not going to worry too much about that. I'm also seeing that there's like these H2s that are likely to get canceled out there. So we need to be thinking about how we're going to get those things to cancel out. Yeah, so let's have a look and see what we're doing here. So I'm seeing that this line 1, yeah, I'm just trying to also see that there's like H3BO3, but I think that that's going to end up canceling out as well. I might be wrong about some of the stuff in this problem, but we'll do a little bit of process and it should end up working out. I'm seeing that there's stuff that's not quite canceling out as is. So I bet we have to end up canceling out some other stuff. Okay. In any case, let's start working on the process of elimination. So if we're rewriting line 1, I'm going to call this line 4 and say that that is a negative of line 1. So line 4 is just going to flip everything. So we've got this H3BO3, and we've got the 3 HCl is now reactants going to form BCl3 plus 3 water molecules. And now that new change in H is a, we're going to flip that. So now it's going to be a positive 112.5 kilojoules per mole. And that looks okay. But I'm going to want to multiply that by 2. So if I look at this, I'm going to say line 5 is equal to 2 times line 4. So we're going to just double everything. And that works out pretty good. And it actually should cancel out some other stuff in our other reactions here kind of nicely. So our new change in H for line 5 is going to be double the other one. So we just take that 112.5, we double that, get 225, positive 225 kilojoules per mole for this reaction. And I can start to then cancel some things out a little bit in these other reactions. So I'm seeing that line 3 actually, it looks to me like this line 3, I was a little bit incorrect when I first said this because I'm looking at line 3 and I'm thinking that we're going to need to multiply that by 6. Actually, because this CL, that was my error where I was looking at that. I was like, wait, hold on, that needs to be multiplied by 6. I'm seeing how like with line 5 that would be useful. So for what I'm going to call this line 6 here, that's going to be 3 times line 3. So, and I think that that would end up giving us close to what we want. So we've got 3H2 plus 3Cl2 goes to form 6HCl. And now that change in H value for that new reaction is going to be 3 times what it was. It is still going the same direction, so it should still be a negative. I see that 184.6. We're going to times that by 3. So we've got negative 553.8 kilojoules per mole for that, and that seems pretty reasonable to me. Oh, actually, sorry. No, we need to multiply this by not 3, but by 6. There's a couple mistakes in here, actually. Like I said, these problems can be a little tricky, but we can check through it and double check our work, and that is always something that I would encourage students to do. I was just looking that we want to get the 6 CLs, and they're not present anywhere else, so that kind of clued me in. I'd also written in times 6 up above, which was important there. So I think whatever we had as our previous number, we now need to just double that. Oop, no, it's the 1107.6. I calculated, just double clicked on that. We could prove that by doing the 184.6 times that by 6. All right, making sure that's still a negative. Yeah, that looks good. So I could even write out 6 times the negative 184.6 just to make sure that that really is plugged in correctly. So I'm looking there, I'm like, okay, well, line 5 and line 6, it looks like these HCl's are going to start canceling out kind of nicely. I am looking, line 2 looks pretty good as is. So I'm thinking let's combine line 5 and line 6. So line 7 now is going to be 5 and 6 put together. And I'm going to maybe also add in line 2 as well as it currently is, because I think that that should cancel some stuff out pretty nicely. So let's go ahead and just do, you could do this as 2 steps, like you could combine 5 and 6 and then get it as line 8 and then add line 8 to line 2, and that would be totally fine. But let's try and do this just 2 steps at once. So we've got that line 5. And that's going to be its reactants. Let's get its products as well. So we've got its components kind of coming in here. I'm going to do a little bit of color coding showing where it came from. And let's just create a little bit more space as well. So we got line 5 is with its reactants products. I'm going to just snip line 6 because we can. So we've got those things being added in as well. And it looks like line 2 now is, we're going to have to write that in because we don't have that written in ourselves. That was just kind of in the problem. So we've got the B2H6 plus the 6 water molecules. And then it looks like on the product side, we're going to have the 2H something BO3s plus 6 H2s. I think it was, what was that? H3? Oh yeah, it's an H3, not an Hg. Okay. Got H3 BO3 and H3 BO3. It looks like 2 moles of that on both sides. So all of those look like those have been combined correctly. I'm just going to do a little bit of simplifying of the reaction, of canceling out the things that are present on both sides. And it looks to me like that works out pretty nicely. So I'm seeing 6 waters as well, so that cancels out, and that leaves us with the 6H2 plus the 6Cl2 plus the B2H6 going to form 6H2s plus 2BCl3s. And I think that that's it. Actually, did we miss? Oh yeah, there's actually also a H2 being canceled out there. So that is not included in our final reaction. I thought so because I was like, why is that H2 still present? So it looks like that got taken care of appropriately. So when we combined 5, 6, and 7 as is, that worked out nicely. So let's do that for its change in H value as well. So we'll have a number for 5, 6, and 2, and they're just being added to each other. This is the power of flipping the numbers. You can just add the signs appropriately. So line 5 was a positive 2, 2, 5. And then line 6 was a negative 1,107.6. And line 2 it looks like we have that all the way up here, negative 493.4. And so we can just kind of do a little guesstimation here and see that the negatives are bigger than the positive. This should be going down the hill energetically. So we see a 225 minus the 1,107.6. And then minus 493.4. Yeah, so we're getting about a negative 1,376 kilojoules per mole of this reaction now. Like I said, this problem is a little bit tricky, and you saw me in this recording have some errors. It's very common in these problems to get a little bit stuck, but if you have good notation, then you should be able to track it back like how I was and able to see how some things canceled out. I would really encourage you to label these lines and write it out and give yourself space. That's the biggest mistake that I've seen when I've been tutoring people on these problems, is that they're just trying to do too much mentally, and they like forget to flip a sign, or they forget to multiply something by 2. And it really is just easier if you just slow down a little bit to do these problems. Thank you for McLearning with me. Before you go, please check out the following services that I offer with my business. So if you click the link in my videos, this goes to my website. I might be changing it from Podia because I'm no longer doing the interactive videos for sale. I might put those up for free. But most of my other services are linked here. So you can see that I've got like a Teachers Pay Teachers and a Wyzant. The Teachers Pay Teachers has a lot of my assessments that I have for like the NGSS, as well as lessons that I made when I was actually a teacher in the classroom. So I've got quite a few things like CERs and other things on there. If you want to get one-on-one live support from me, either like with science or like working on like teaching support lessons and that kind of stuff, you can sign up through Wyzant. I have a link to there where you can contact me there, and we can schedule hourly appointments. And I've got a few other things on here like a Facebook page, and other social media. And if you're interested in getting professional development with me for like a team of teachers, a whole page with information on that. So yeah, feel free to check that out. Thank you.